So we've taken a look at continuity over the real numbers, over an interval, and at a point. And the whole purpose of that was to kind of prepare you for what I like to refer to as the composite function theorem of limits. And so what this theorem essentially states, I mean, it doesn't really have a formal name, but I just kind of like to refer to it as that. It says that if we have a function f of x, which is continuous at a point, x equals L, such that the limit as x approaches a of g of x equals L, and of course this L over here has to actually exist, then the limit as x approaches a of f of g of x, right over here, so the composition of these two functions, is equal to f of the limit as x approaches a of g of x. So you can kind of think of like taking this limit and inputting it into, kind of like taking the limit and putting it into the function, if you will. And then that's just going to be equal to f of L right over here. So the condition for this statement over here to hold true is that f has to be continuous at L, and the limit as x approaches a of g of x has to be equal to L, and it has to exist, of course. And so what we can do is, if you want to take a look at an example over here that I illustrated, and so essentially we have two functions. Here's our function g of x, here's our function f of x, and we're asked first of all to find the limit as x approaches -4 of f of g of x. And so what we can do is we can take a look right over here at g of x, and we see, you know, at -4, we're kind of approaching +3 from the values that are less than -4, and from values that are greater than -4, we also seem to be kind of converging to +3. So we can say right over here, if you want, we can say that the limit as x approaches -4 of g of x is going to be equal to 3. And so this value right over here, this exists, right? So the limit does exist. And it's equal to +3. And then we can go ahead and we can look at our function f of x, and we see that we're continuous at this point, right? Because, you know, if you looked at the definition of continuity at a point, you would see that it holds for x equals 3 when we're looking at f of x over here. And so then we can say that this limit is going to be equal to the limit as x approaches 3 of f of x, if you want. That's another way that you can even write this statement, which is just going to be equal to f of 3 in this case, right? And f of 3 looks to be +5. So we can then say that this limit over here is going to be equal to +5. And then another limit that we can take a look at is the limit as x approaches -3 of f of g of x. And then here we're going to run into a bit of a problem. We can, you know, already anticipate that. I picked this number particularly, although the graph is not really drawn to scale. And so essentially, if we're looking at the single-sided limits for g of x as x approaches -3, from values that are less than -3, we seem to be approaching this value over here. This looks to be, I don't know, maybe this is like 6 or maybe 5, I don't know. So we'll put like a question mark. And then if we look at the values that are greater than -3, we seem to be converging to this one point over here, which looks to be about 1, for example. I don't know. And so the one-sided limits don't agree with each other. And if you recall, quite a while ago, we said that if the one-sided limits don't agree with each other, then we have kind of a jump discontinuity, which is very evident from the graph. It seems like we're kind of jumping from 6 down to 1 as x approaches -3. And so essentially, we can say that this limit, the limit as x approaches -3 of g of x, this thing right over here does not exist. Does not exist. And because of the fact that this doesn't exist, this disobeys this first condition over here. We said that this has to be equal to some number L, and it has to obviously exist. And so then we can say that this limit, by extension, does not exist. The limit is x approaches -3 of f of g of x, because we're inputting, you know, we can't, you know, just take the limit and put it into the function. Instead, we have a, you know, we're not defined, or not necessarily not defined, but our limit is not defined as x approaches -3. And so then we can go ahead and look at another example. This one looks a little bit more intense, but it is quite a nice example. So we're taking the limit as x approaches infinity of sine of this crazy rational function. And so essentially what we can do is we can think, let's try to figure out the limit as x approaches infinity of this rational function over here. It's pi x squared minus 7x plus 10. And we're dividing that by 2x squared minus 100x. And if you remember how we take limits at infinity, which I'm hoping you do, we kind of just look at the dominating term here. And so as x approaches infinity, you know, x squared and any constant times x squared is going to dominate over all of these terms. So we can kind of ignore this -7x, ignore this 10, ignore this -100x, and say that this is going to be equal to pi x squared over 2x squared. And then we see that this cancels out quite nicely because, you know, you have the x squared and the x squared, so it's just going to be pi over 2. So as x approaches infinity, this rational expression is just going to converge to pi over 2. So then we can say that this is just going to be equal to sine of this limit over here, but we were able to determine the limit. We said this limit is going to be pi over 2, right? And we know that sine of x is continuous over its domain, and so then we can say that sine of pi over 2, or the limit as x approaches infinity of sine of, of this crazy function over here, is just going to simplify to sine of pi over 2, which we know is going to be equal to 1. So as you can see, if we can establish this statement over here, if we can establish these conditions where f is continuous over its domain, or continuous at L in particular, actually, and if we can make this statement over here, then it's very easy to evaluate these very intense kind of composite functions, whether it's through the graph or through the equation of the function.